All right, here it is. It turns out the alternating series has a bonus feature to it. It's called the alternating series remainder. And if you're like most math students, calculus students, whenever you hear remainder mentioned as part of an idea, you cringe, right? Like, oh my gosh. Calculating a remainder, like an error, it usually implies some awful formulas, like we saw with the midpoint rule, the trapezoidal rule, Simpson's rule, and it's there's usually no fun at all. But here we go, the alternating series remainder. The theorem says if an alternating series converges, so if we know that it converges, and the sum S is approximated by the nth partial sum Sn. So here's what's cool. We're not saying we know what the sum is, but we could approximate it with an nth partial sum, right? We could do the long work and add up a bunch of terms on our own. So if it converges, we know that capital S exists, and there's some nth partial sum that we could calculate in theory, right? Then here's what would be true, right? So if you were to take the difference between the actual sum and the nth partial sum, the approximation, we're going to call that R of n, or excuse me, R sub n. We throw absolute values on because we always think of a remainder or an error as being positive, like a distance. So whatever the error is, let's just give it a new name. That difference is R sub n. And this is the cool part. It's always less than or equal to the value of the next term after we stopped taking the partial sum. So if we take the partial sum up to n, then if we take one more term, that remainder is always less than or equal to that next term. All right, I got to give you a visual on this because this is not clear at all. But when you see the picture, hopefully you're like, oh yeah, okay. All right, so what I've done here, I've drawn a graph of a possible series. So I've graphed S sub n here at the top and the n terms here on the horizontal. Okay. So the nth partial sum might do all kinds of things as we add more terms on, right? So I'm saying the first partial sum, which is really just the first term, let's say it's up here. The second partial sum now drops. Why? Because it's alternating, right? So that first term is positive, let's say. Then the second term would be negative. So when we add it on, it's going to drop the total. Hopefully that makes sense. Then the third term would be back to positive. So we're going to add that and it's going to jump up. But then the fourth term is negative. So that means when we add it, it's going to bring it down. Okay. Also, we were told at the beginning of that theorem that this alternating series converges. So that means there's some capital S out there that all of these partial sums are headed towards. So if we were to take the limit of the partial sum, it would zone in on this S. And I've drawn a dotted line there. It's not coming up all that well, but I think you can kind of see it. Okay, so hopefully so far so good, right? The terms are alternating, so I had a positive. When I add the negative, I add the positive, I add the negative, and it would keep doing this kind of jumping back and forth over that dotted line. Why would it jump back and forth over the line? I was told, again, because it converges, I know the first condition right, is that the limit of these terms goes to 0. So they're getting smaller. There are two things going on. The terms are getting smaller, and they're going positive, negative, positive, negative. So that whatever this height was, I know the next term is going to be negative and less than that. So it doesn't bring me all the way back to 0 or beyond. It's still going to be positive. That first term dictates whether the total sum is positive or negative. Since this one's positive, I know the sum will be positive because I'm not going to go down all the way. Then the next ones I'm going to add, but it's not going to get me as far away. You know, if we think of these little distances, these distances to S are shrinking each time because the terms are getting smaller. So I jump to the other side of the dotted line, but that distance shrinks, and I jump and the distance shrinks. Okay, then like skip ahead to the nth term. By the time I get out to the nth term, wherever that is, I could be on either side of the line, I don't know, but whatever that's going to be, it's going to be tiny. It's going to be this tiny little gap. Let's think about where n plus 1 would fall, the next term. Wouldn't it be on the other side of the dotted line? It's got to be. That's how this works. They always jump over, but they just zone in on it. So if going to the n plus 1 causes me to jump to the other side, then I know the value of n plus 1 had to be bigger than the remainder back here, right? So the remainder, like the error, is this little distance, but n plus 1 caused me to jump further than that. So if I can figure out the value of that term, how far I jumped, I know the error was something less than that. Okay, hopefully that makes sense. Let's take a look at an example. Now these get pretty cool. And they're not too terrible to solve, right? The key is knowing how to set it up. And once you see one of them, that it's really not that bad. I try not to use that sort of language as a teacher. Hey guys, this is easy. In this case though, once you see it compared to other remainder things, this is a lot less intense. That's probably a better way to say it. All right, here we go. How many terms are needed to approximate this beast? Let me pull it over a little bit so it's more clear. N equals 1 to infinity, negative 1 to the n, all right, over n factorial. We're going to approximate that to, I think I forgot a word here. It should say within. How many terms are needed to approximate this to within 0.001 of its sum? I have no idea what that adds up to. If I was to apply the alternating series test, it would converge. That's really not said here. It should have been. But that's going to converge. So how many terms do I need? 10, 20, 100? How many terms of this do I need so that it comes within 0.001 of its actual sum? And that'd be, then we could add up those, how many terms that is, and have a really good approximation. Okay. Well, let's see here. Here's what we're going to do. We're going to note what the a sub n is, right? The non-alternating part. And then we're going to think, all right, so the next term after a sub n, if it's going to be within 0.001, then a sub n is going to be less than or equal to that. So this value needs to be smaller than or equal to what we need it to be within. Then I'll know the remainder is less than this. So the remainder is definitely less than that. Hopefully that logic is clear. All right, we can sort of maybe even write all that in. I know the remainder is less than this, so if I make this less, then I'll have it. And then the question is, right, how many terms? What is n? How many terms do I need to make a n sub n plus 1 less than or equal to that number right there that I'm told? All right, well, here's what we'll do. We'll set up. We'll go for it. If that's my nth term, here's my n plus 1th term. I replace the n with n plus 1. It's got to be less than or equal to that. Now, normally, we would solve, right? We would multiply both sides and divide and do. Because there's a factorial, there's no way to reverse a factorial. So don't do that. In this case, we're just going to guess and check. So we're going to plug in a value of n and see if it works. And if it does, great. If it doesn't, we're going to try another one, until we can hone in between exactly what n needs to be. So let's try n equals 5. Plugging it in right there. If n equals 5, I've got 1 over 6 factorial, and that's what happens. I get 0.0014. But that is not less than 0.001. It's actually a little bit bigger. Okay, so it's not 5. But that's pretty close, right? Again, how did I know 5? I just guessed something. And I'm kind of cutting right to the chase here in this example. But, maybe I would have guessed like 10 to start it off, 10 terms. And then I realized, oh, that's too much, and I would have scaled it back. N equals 5 comes right up on the edge. N equals 6 is going to do it. So that'd give me 1 over 7 factorial, which is this. And yep, that worked. Not only did it work, but the one previous to it did not work. So I know I need exactly 6 terms for this to happen. 5 wouldn't be enough. 6, I get it. If I was to go 7 or 8 or 9, I would get it. But I don't need that many to get it within, to approximate that closely. I can stop at 6. If it had been possible to just solve this as normal, we could have done that too. And then, right, you'd have to round up if you get a decimal to get to the next highest value of n. But with that factorial, no, we can't do that. Guess and check. All right, that's the end of alternating series.